Hello, my name is Anthony, and this is my Lab 5 report. So the purpose of this experiment was to measure how long it takes a bar magnet to fall through a tube of aluminum foil. The fundamental physics principles used were the Biot-Savart law for a magnetic dipole, Faraday's law, and Ohm's law, both for which the equations are shown. And then for the model, I used a code to model the bar magnet falling through the tube, and for the result, the experimental time was 0.944 seconds, and the computational time was 0.852 seconds. So the model uses a code to model the tube as a large number of current rings, and then it uses the Biot-Savart law to calculate the magnetic field of the magnet, and also it uses the magnetic moment of the bar magnet calculated in Lab 3. Finally, the model calculates the force on the bar magnet at every 0.001 seconds and uses that to measure the velocity, position, and total time of the magnet. The assumptions I used for this experiment are that the tube is uniform all around and that the magnet only experiences the force of gravity and the magnetic force. This makes sense because the tube is very close to being uniform and the air resistance has a minimal effect on the net force of the magnet. This is also used to prevent the calculations from becoming overly complicated. And in the experiment, the magnet is the system and the tube and the earth are the surroundings, and the initial conditions are listed at the bottom of the slide. For the experiment, first we used the physics toolbox magnetometer to find the north pole of the magnet. And then we used a meter stick to determine the length, width, and inner radius of the tube with the values shown. And finally, we used a scale to measure the weight of the magnet to be 0.023 kilograms. Then we dropped the magnet down the tube and measured the amount of time the magnet was in the tube. An example video is on the right. We determined that the magnet fell slower than in free space, and this is because the aluminum gets emotional EMF from the magnet and in turn causes an upwards force on the magnet. However, we could not use a ferrous tube as ferrous tubes cannot conduct current. We took 5 trials of the experiment shown on the table, and the average time for the magnet was 0.944 seconds. Now onto the code, the link for which is in the description. The first part of the code defines the initial conditions and the dimensions of the tube, and the next part creates the tubes as a large amount of rings. Then the magnet is defined with the measured weight and the magnetic moment determined in Lab 3, and then next comes a function to calculate the magnetic field, which is also from Lab 3. Afterwards comes a function to calculate magnetic flux through a ring, and then for every 0.001 seconds, the code calculates the current and magnetic force on the magnet for every ring. Then the code sums up the magnetic forces of the rings to get the magnetic force of the tube and finds the net force by adding this with the force of gravity, and then it uses this to calculate the magnet's position and velocity, and this is repeated until the magnet comes out the bottom of the tube. Finally, the code displays the time it took for the magnet to go through the tube. In this case, that was 0.852 seconds. In the simulation, blue was above the magnet and red was below the magnet. Then, using Lenz's law and the right-hand rule, I determined that blue meant counterclockwise current and red meant clockwise current. However, when I flipped the magnet, the red and blue sections flipped sides, but the amount of time remained the same. This meant that the counterclockwise and clockwise current also flipped sides. The computational and experimental time values are similar, but the computational value is likely more accurate because there were errors in the experimental value. I'll talk more about this at the end. And the velocity time graph is linearly decreasing, which means that the forces acting on the bar remain constant as the magnet falls through the tube. To answer the first question, this would cause the current going through the conductor to drastically increase, and this would cause the upwards magnetic force on the bar to drastically increase. As a result, the magnet would either start floating in the tube or likely even come out of the top of the tube. To answer the second question, this would cause some of the ring currents to be zero as those rings would no longer have full loops. And as a result, it would reduce the total current in the tube, which would reduce the upwards magnetic force on the magnet. This would cause the magnet to fall faster. And if enough holes or slits are made, it could even cause the magnetic tube or the conducting tube to have no effect on the magnet. In conclusion, the experimental and computational times were similar but still different. Both the model and experiment had the same assumptions, initial conditions, and magnetic moment, so the same setup. However, the model calculated time using the net force on the magnet at every 0.001 seconds, while a timer was used to calculate the experimental time. However, as said earlier, the experimental value is also less accurate due to human error. This came partially from the fact that the magnet was not dropped from the exact same height after each trial, and also that there was some error when measuring the time, as there is a reaction time between when the magnet comes out of the bottom of the tube and the stopwatch being stopped. Therefore, it makes sense that the experimental time is greater than the computational time. However, overall, the experiment was successful at finding good approximations.